So, think about the exact millisecond you flip a light switch in your home.
Right, just a totally normal, everyday action.
Exactly. We operate under this basic assumption that it's just a simple binary transaction. You flip the switch, electricity flows along this nice predictable path, and boom, the light turns on.
Yeah, it feels instantaneous and perfectly clean.
But if you were to slow time down to that single microscopic millisecond, you wouldn't see a neat, orderly process at all.
Not even a little bit.
No, you would be looking at a state of violent, chaotic electrical anarchy.
It really is the ultimate dynamic transition. I mean, for a fraction of a second, the fundamental rules of physics that we rely on, the ones that literally keep our power grid stable, they just completely stop working.
It's wild.
It is. The materials themselves fundamentally change their nature.
Well, welcome to the deep dive. Our mission today is to basically strip away those oversimplified, comforting rules of electricity you might have learned in basic science classes.
Yeah, the stuff they teach you in high school.
Right. We are going to look at the explosive reality of what actually happens the exact moment a circuit wakes up.
And we are pulling our insights today from this brilliant dive into the physics of transients. It's specifically focusing on the dynamics of variable circuit constants.
Which sounds incredibly dense.
It is a bit heavy, yeah. It explores what engineers see when they hook up these high-speed visual graphs, they're called oscillograms, to capture those chaotic split seconds.
And don't worry, we are leaving the really dense mathematical equations behind today.
Oh, absolutely. No live math on this deep dive.
Thank goodness.
Yeah.
We are just here to extract the pure aha moments, to really help you understand the hidden reality behind the walls of your house.
Right, because in basic physics, we are taught that a circuit has constants.
Like literally called constants.
Exactly. Things like resistance, inductance, conductance, and condensance, which, by the way, is just another word for capacitance.
Right, we treat them as fixed numbers.
But during a transient period, like that exact moment you open or close a switch, these elements are not constant at all.
They vary wildly.
Yeah, they behave more like living, breathing variables reacting to extreme stress. The moment energy is suddenly introduced or removed, the physical properties of the wires and even the surrounding environment are thrown into absolute chaos.
Before they finally settle down into those predictable constants we recognize.
Exactly.
Okay, let's unpack this, because talking about transient periods and circuit constants can feel a bit abstract.
Yeah, it can get very theoretical very fast.
So let's start with something incredibly tangible, like a standard tungsten incandescent light bulb.
Perfect example.
We walk around with this assumption that the metal wire inside a light bulb simply resists electricity at a steady fixed rate.
Right. You put a certain amount of electricity in, you get a certain amount of resistance pushing back.
But the problem with that assumption is that it ignores the single most destructive force to electrical stability, right?
Which is temperature.
Temperature.
Yeah, for metals, specific resistance is actually a linear function of temperature.
So as one goes up, the other goes up.
Exactly. When you force electricity through a cold piece of metal, friction happens at the atomic level, generating immense heat. And when that temperature changes rapidly, the physical structure of the metal's resistance changes just as fast.
I was looking at the actual timeline for a tungsten lamp, and it is staggering.
It really is.
When you first flip the switch, the filament is just sitting there at room temperature. Its resistance is remarkably low.
And because the resistance is low, a massive flood of current rushes in.
Right. But it only takes 0.02 seconds.
That's 20 milliseconds.
Which is faster than the blink of an eye or, a camera shutter. It takes just that long for that wire to reach full blazing incandescence.
And in that tiny 20 millisecond window, the resistance of the tungsten filament skyrockets by 400% from its initial room temperature value.
400%?
Yeah, it's a massive wall.
It is like you start driving down a perfectly clear highway at top speed, and within 20 milliseconds, the road just turns into waist-deep mud.
That is a great way to picture it. The environment fundamentally changes.
And because the resistance spikes so violently, that initial massive flood of current is rapidly choked back down to a normal operating level.
But then you contrast that with a completely different material, like carbon.
Right, which behaves totally differently.
Completely opposite. If you look at an incandescent carbon lamp, you see an entirely opposite reaction because carbon has a negative temperature coefficient.
Meaning, instead of the resistance going up as it heats up.
The resistance actually goes down.
Wow. And it takes much longer to settle, too. I read it takes about half a full second for the carbon filament to reach a stable temperature.
Yeah, a lot slower than tungsten.
But when it finally does stabilize, the resistance is only about 70% of what it was when it was cold.
Right. It becomes a much better conductor the hotter it gets.
So you have two different materials reacting to the exact same electrical trigger in completely opposite ways.
It entirely obliterates the idea that resistance is just a fixed number printed on a spec sheet.
It really does. It is entirely at the mercy of the heat of the moment.
And that brings in a really fascinating complication when we talk about alternating current or AC power.
Oh, right, because DC power is one thing.
Yeah, in a direct current system, the temperature reaches a constant state and just stays there. But on an AC grid, the power is pulsating. It surges and drops in a continuous wave.
Which means the power supplied to the lamp pulsates at double the frequency of the current itself.
Exactly. And that pulsating power means the heat being generated inside the filament is also pulsating. The physical resistance of that metal wire is continuously throbbing in real time.
Okay, wait, I have to push back on this a little bit.
Sure, go for it.
Because if AC power is pulsating, say, 120 times a second for a standard American 60 hertz system,
Right.
wouldn't the sheer thermal mass of that filament just average all that out?
You would think so.
I mean, how does a solid piece of glowing metal cool down fast enough between those microscopic pulses to actually change its resistance? It seems impossible.
What's fascinating here is that the filament doesn't need to cool down completely. It only needs to drop a microscopic fraction of a degree.
Oh, really? Just a fraction?
Yeah, you have to picture the energy exchange happening. The lamp is continuously generating heat, right? But it is also desperately radiating that heat outward into your room.
Like it's constantly bleeding energy.
Exactly. So the instant the AC power wave dips, the internal heat generation dips, and for a fraction of a millisecond, the outward radiation actually wins the tug of war.
Wow. So the resistance really is literally vibrating.
It vibrates so violently that engineers can actually measure it using something called a bridge circuit.
A bridge circuit.
Yeah, think of a bridge circuit like an ultra-sensitive balancing scale for electricity. If you put a tungsten lamp on one side and a carbon lamp on the other, you can balance the scale perfectly.
Okay, I'm with you.
But because tungsten's resistance goes up with heat and carbon's goes down, those microscopic high-speed thermal throbs actually tip the scale back and forth, completely unbalancing the circuit.
That is insane. So
Yeah.
to your naked eye, the light in your living room looks perfectly steady.
Perfectly smooth.
But down at the atomic level, the circuit is just managing a state of high-speed, violent chaos.
Precisely.
That completely changes how I look at a light bulb. But I mean, we have this controlled heat inside a glass bulb, safely changing the resistance. But this naturally pushes us to ask, what happens when the heat isn't safely contained in a bulb?
Yeah, when it escapes.
Right. What happens when the electricity creates its own path? And I think this moves us out of resistance and into the realm of inductance.
Which is essentially how a circuit manages magnetic energy and, well, chaos.
And this brings us to the electric arc.
Right. An arc is basically electricity deciding it no longer needs a wire. It jumps through the air and turns that air into superheated plasma.
Which is terrifying.
It is. And an arc behaves very much like the carbon filament. As the temperature of the arc rises, its resistance drops.
Which is a terrifying physical mechanism. I
Yeah.
mean, the hotter it gets, the less it resists the electricity.
Right.
So it lets more electricity through, which makes it even hotter, which drops the resistance even further. It's just a runaway feedback loop.
Exactly. Left to its own devices, an arc is inherently unstable. It will completely consume the system.
So how do you stop it?
Well, to maintain a continuous controlled arc, like in industrial arc welding or old street lamps, you have to introduce a ballast into the circuit.
A ballast.
Yeah, on AC circuits, this ballast is an inductance placed in series with the arc. As the arc's resistance wildly drops, the inductance reacts to that sudden surge by inducing a countervoltage. It acts like an invisible shock absorber to stabilize the flow.
Okay, but arcs aren't just for welding, right? In commercial power systems, the most common place you see an arc is when you are simply trying to open a switch to turn something off.
Yes, you break a circuit while a heavy load of power is running through it, and the electricity just refuses to stop.
Because it has momentum.
Exactly, especially if there is magnetic energy stored in the system. As you pull the metal contacts of the switch apart, the electricity jumps the widening gap.
And in that exact moment, the resistance of that air gap isn't constant.
No, it shifts from practically zero when the contacts are touching, stretching desperately toward infinity as the gap widens.
Until the arc finally snaps and the circuit breaks.
Right. Managing that kind of magnetic momentum is why the concept of variable inductance is so critical.
Especially in ironclad circuits, like the massive transformers that power our neighborhoods.
Yeah, transformers are a whole different beast. We are taught in physics that a magnetic field, the magnetic flux, is perfectly proportional to the electrical force you push into it.
Like you push 10 units of electricity in, you get 10 units of magnetism out.
Right. But in iron, that rule completely falls apart.
Really? How so?
Iron introduces a property called permeability, which is basically a measure of how willing the metal is to let magnetic lines flow through it. The resistance to that magnetic flow is called reactivity.
Okay.
But in iron, that willingness actually changes depending on whether the magnetic force is currently increasing or decreasing.
So it lags.
Yes, this lag creates a phenomenon engineers call a histeresis loop.
Okay, a histeresis loop. If you look at a visual graph of this, it's not a straight line at all, is it?
No, it looks almost like a squashed S shape that loops back over itself.
Right. It charts the fact that the iron core actually remembers its previous magnetic state. It is basically a visual map of magnetic memory.
And the magnitude of the chaos when you flip a switch on a transformer depends almost entirely on this memory.
How does that work?
Well, if you completely erase all the residual magnetism in the iron core, and you perfectly time the closing of your switch to hit the exact peak of the incoming voltage wave, you get zero starting transient.
The current just flows smoothly.
Exactly. Smooth as silk.
But we don't live in a perfect world.
Not at all.
Out on the grid, that iron core almost always has residual magnetism left over from the last time it was used. Like it remembers.
Yeah, it really does.
It's like someone holding a grudge. Like if you walk up to someone and they are already angry, that's your residual magnetic flux, and you push them in the exact direction they're already angry, they hit their saturation point instantly.
Oh, absolutely.
They absolutely explode.
I love that analogy because it perfectly describes magnetic saturation. When you push that iron core in the same direction as its residual grudge, The permeability of the iron just vanishes. The core saturates.
And what happens then?
When an iron core saturates, its inductance, its ability to act as a buffer and manage the current, plummets to near zero.
So the shock absorber completely disappears.
Completely. And when that magnetic threshold is crossed, the very first half cycle of the current wave floods the system in a massive, steep, destructive spike.
Wow.
It is a violent transient that the standard mathematical equations completely fail to predict.
Right, because the math assumes the metal behaves logically.
Right.
I know there's an equation called Frillich's formula, which tries to tame this.
Yes, Frillich's formula.
It assumes that the magnetic resistance, the reluctivity, is a nice linear function based on how much magnetizability the iron has left.
But Frillich's formula is merely a polite suggestion that physical metal routinely ignores.
A polite suggestion.
Truly, if we connect this to the bigger picture, this is precisely why electrical engineers cannot rely solely on mathematical models when designing the power grid.
Because the math just breaks down.
Yeah, no perfect mathematical expression exists to fully map the complex, chaotic reality of a hysteresis cycle. The true physical loop is just too messy.
So what do?
Engineers actually have to rely on experimental oscillograms, those high-speed visual wave graphs we mentioned earlier.
Oh, okay.
They need to see exactly how the metal misbehaves when pushed past its limits because, like we said, the equations fall apart.
It is wild that our entire modern grid relies on materials that basically refuse to follow the math.
It keeps engineers on their toes, that's for sure.
So we've looked at wires heating up and changing resistance. We've looked at transformers holding magnetic grudges and losing their inductance. Yep. But both of those happen within the system itself. What happens when the electricity decides to escape the system entirely?
That is a whole different ballgame.
That brings us to our final two variables, conductance and condensance, which rely entirely on the environment outside the wire.
Right. Let's look at conductance first. When engineers calculate power transmission lines, they usually treat conductance as practically zero.
Because of the insulation.
Exactly. The insulation, whether that is thick rubber shielding or just the empty air between the wires, is doing its job. It prevents the electricity from leaking out.
But insulation fails.
Yeah.
I mean, a tree branch hits a line or the shielding deteriorates, creating an arcing ground.
And when that happens, we are talking about a physical breakdown at the molecular level.
The physical breakdown of the air itself.
Right. This is a process called ionization. The extreme electrical stress literally rips electrons away from the molecules in the air or the insulation. The environment is instantly transformed from a perfect insulator into a highly conductive plasma bridge. The conductance of the circuit spikes from 0 to infinity in a microsecond.
And the resulting chaos is massive. These momentary short circuits are like prolific sources of electrical transients.
Yeah, they give rise to violent oscillations that produce high-frequency waves.
It is exactly like dropping a massive boulder into a calm pond. The ripples just violently crash into every other connected piece of equipment on the grid.
Which perfectly transitions us to the final variable, condensance or capacitance, which is essentially the circuit's ability to store electrical charge in the space around the wires.
Right, and under normal everyday conditions, the air surrounding a high voltage wire is an excellent insulator.
But there is a hard mathematical breaking point. When the voltage gradient pushing outward from the wire exceeds 29.8 kilovolts per centimeter.
29.8 kilovolts.
Yep. The surrounding air physically breaks down. It reaches its limit, the air molecules ionize, and it produces a visual corona.
Like, the air around the wire actually glows with a faint violet light, right?
It does. But this glowing corona isn't just a fascinating visual phenomenon. When that air starts glowing, its fundamental conductivity changes.
How so?
That space filled by the corona actually becomes semiconducting.
Here's where it gets really interesting. Because you're saying that glowing air immediately surrounding the wire is now conducting electricity.
Exactly.
So essentially, at 29.8 kilovolts, the wire grows a ghost wire made of glowing charged air around it.
Yes. That is a perfect way to describe it.
And the entire circuit suddenly behaves as if the physical metal is significantly thicker than it actually is.
That's it, exactly. The effective size of the conductor expands into the air itself.
That's crazy.
And this fundamentally changes the geometry of the system, which changes the condensance of the entire circuit.
And just like the microscopic throbbing of the light bulb filament we talked about earlier, this ghost wire isn't stable either, is it?
No, not at all. Because these are alternating current transmission lines, the voltage is rising and falling in a continuous way.
Right, it's pulsating.
So that visual corona, that ghost wire, only appears near the absolute peaks of those successive voltage waves, precisely when the voltage crosses that 29.8 kilovolt threshold.
Oh, I see.
As a consequence, the condensance of the circuit is pulsating. It throbs at double the frequency of the voltage.
So the wire is literally breathing. It is expanding and contracting electrically dozens of times every single second.
Now imagine feeding a perfect, smooth sine wave of voltage into a system that is breathing like that.
You would expect a perfect wave of charging current in return.
Right, but because the condensance is dynamically changing during the cycle, the returning wave shape gets completely warped and distorted.
And it isn't just the voltage causing the warping either, is it?
No.
Because I saw there was this incredible oscillogram data showing how environmental factors completely rewrite the rules.
Oh, the environmental stuff is fascinating.
Like, if a transmission line gets covered in a layer of snow, the physical surface geometry of the conductor changes, which changes how the air breaks down.
Exactly.
Or if a strong wind is physically swaying the wires closer together, the electrical gradients shift in real time.
This raises an important question about the staggering complexity of managing our modern infrastructure.
Yeah, it really does.
We attempt to map these sprawling power grids using clean, predictable constants. But out in the messy real world, a sudden gust of wind or a drop in temperature can fundamentally alter the size of that electrical ghost wire.
Just completely change the game.
Yeah, it warps the electrical wave in ways that a textbook equation sitting on an engineer's desk could never possibly predict.
It really is staggering.
Yeah.
So what does this all mean?
Right.
I mean, we started this journey looking at the fundamental constants of electricity. Resistance, inductance, conductance, condensance.
Right, the constants.
We treat them like the sturdy bricks holding up our technological house. But the reality is, these mathematical constants are really just variables in disguise.
They behave perfectly nicely right up until the system undergoes a transition.
And in those split-second, transient moments, everything changes.
Yeah, the microscopic temperature of a metal filament, the magnetic grudge held by an iron core, and the glowing, breathing air surrounding a power line, they completely take over the physics.
The scientific rules are only rules until the environment decides they aren't anymore.
Precisely.
So